In this video, we're going to continue with the exceptions to electron configurations by taking up the examples of the iron ions. Our goal is to first do the neutral iron and then to write the ion exceptions. If we go up to our periodic table, you'll notice that iron is not in group 6 or group 11. It's over here in group 8, so it's probably not going to be one of the exceptions to the rules that we saw, but maybe its ions will be, and we'll take a look. So we have iron to be 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and then 3d1, 2, 3, 4, 5, 6. So eventually you'll become that quick and efficient at doing it as long as you have more practice. But let's go ahead and write iron out. As we said, let's iron this out. Lame joke. To keep things light a bit, here we go. We have 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and 3d6. And this is not one of the exceptions. It's not in group 6 or group 11, so we don't have to worry about it. And you can also see clearly that we have a full shell and a partially filled. If you move this one electron from 4s2 into the 3d6, it becomes 3d7. So we have half full and partially full. So it still doesn't really improve the stability, so this is fine the way it is. So let's go ahead and write that iron configuration in an energy level diagram over here. Just like this. Which is fine and stable. But now we need to go make the iron 2 plus ion. And remember that when you're making ions for cations, you generally remove the highest energy level S, level P first, if that's there. If it's not there, you'll then remove the S and then remove the D following that. So highest level P, then S, and then afterwards D at the next level that's there. And then you'll just kind of cycle through that as you go. So we're going to remove the highest level electron in total. The highest level that we have here is at 4, energy level is 4, but there's no P, there's just an S there. So we're going to be removing these 2 electrons over here to make Fe2+. And so that would give us 1s2, 2s2, 2p6, 3s2, 3p6, 3d6. And if we were going to continue to remove electrons, we'd then remove from the D and then kind of cycle through that way. But right now we just have to remove 2. Now you'll notice this looks fairly straightforward so far. This would be the ion that forms, but this is actually not the most stable it could be. What we're going to do is we're going to form this ion here. So I'm just going to form it by removing the 2 electrons from the 4s here. And you'll notice that the reason this is not as stable as it could be is because the last shell that we have there, the last subshell, is partially filled. Now we could actually take this electron here and put it into the 4s that was, it's now vacant, that was empty because we removed 2 electrons, and have 1 electron in there. And so it would look something like this. 1s2, 2s2, 2p6, 3s2, 3p6, 4s1, 3d5. And so what we've done by doing this is we've created 2 half-filled sublevels. And so these are more stable than the partially filled one that was there before. So this would be the better electron arrangement than this one over here for the iron 2 plus. Now, if we want to create iron 3 plus, we just need to remove 1 more electron from the iron 2 plus. So remember, we always want to remove from the highest energy levels first. And so if we were starting from the neutral iron, we'd remove from the highest energy level 4, So that's 4 there. If there was a P, we'd remove from 4P first, but there's no P there. So we're moving from S, and then we're going into the D's after. And then we'd start cycling again if we're removing more, but no, we're not. We're just removing from the S and then the D. So we'd remove the 2 from the, let's make it a different color. We'd remove the 2 from the S over here. That would make it 2 plus, but we need to remove one more, and that one more would come from the D over here. And so that would be our 1s2, 2s2, 2p6, 3s2, 3p6, 3d5. And this doesn't need to be rearranged. This is half full, so that's pretty stable. If you were building this from the Fe2 plus, you'd simply remove from this 4s1 over here. And that gives you a nice stable 3d5 at the end there. And so this is an example of a transition metal that can form more than one charge. And the reason it can form more than one charge is that it has access to the d electrons as some of its valence electrons. So it can get rid of the s electrons from the valence electrons, but also the d electrons. So as we saw in a previous video, the transition metals, their valence electrons are basically the highest energy, we'll call this highest energy here, highest energy S, and then also the energy level just before the highest energy, we'll call it n-1, D. So you remove from S and you remove from D. Whereas in other metals, like let's say a group 1 or group 2 metal, their electrons or valence electrons we're removing from are the highest energy S, and that's essentially it. If you were in metals that fall into your P block, so around here, for example, group 13, group 14 area, like that, metals that fall into your P block that lose electrons, their valence electrons are typically going to be the highest energy N or S and the highest energy P. And so you'd remove from the P first and then the S. For the group 1 and 2 metals, you remove from the S, the highest energy S. And then for the transition metals, you would typically remove from the highest energy S and then from the D thereafter. Not so much from the P because it's not found in the highest energy level there overall. But again, the reason transition metals can experience several charges oftentimes is because they have access to those d electrons as valence electrons, and they can further lose those. And so this was just an example of making an electron configuration for the iron ion 2 plus and 3 plus. 3 plus wasn't really an unexpected situation. It was mostly the 2 plus where we could make a better arrangement by getting a half full 4s1 and a half full 3d5. So we're just going to finish off this lesson by taking a look at these little diagrams here called orbital diagrams. Orbital diagrams are essentially just like the energy level diagrams, except they're drawn horizontally. They're not drawn with their energies increasing, so from bottom to top. They're drawn horizontally in the increasing energy order. So smallest energy level here, and then smallest energy level, and then largest energy level over here. But you'd fill it up in much the same way, following the same rules. So the magnesium atom, for example, would be 1s2, 2s2, then we fill up the 2 p's there. This has 12 electrons, by the way, based on our periodic table. So far we've drawn 10, and then 3s2. So very similar to energy level diagrams, just drawn horizontally instead, from the lowest to the highest energy in a horizontal fashion. Different representation, same concept overall.